Just a few seconds. Yeah, now we can go ahead.
Okay, sir.
So thank you once again for asking me to say a few words about the speaker. And I saw also the last parts of last two lectures and see that Professor Kumarasan and Professor Balasubramaniam has already told few things. They know, I know him about 41 years now, Professor Ilangovan.
42.
Yeah, and they know at least 4 years more than that. And both his mathematics, about his bridge and all, people have already told a little bit. Let me repeat a bit. Those who has seen the photograph of his taking something prize from none other than this
Gavaskar.
yeah, Gavaskar. And there you see his young day handsome photograph, and already one of his fans he has written that maybe Ajay Devgan learned something from him, his style. So anyway, these lighter things apart, now let me come to the academic thing. First, few things about Kari leaf. See, my association with NBA, this MTTS, from where this Kari leaf has emerged, that is I lectured many times, and I used to conduct a follow-up program in Allahabad, and I learned many things from this MPTS program. Professor Kumaresan, he put lot of effort in building up this thing. It was a visionary thing, and it has helped because you cannot, I mean, really, as days go, we can see the benefits of MPTS program. And we heard from Professor Kumarasan about real curry leaf, the benefits of curry leaf. Now I think time will come to tell about benefits of this present curry leaf. I think this will go a long way to do something. And now coming back to Professor Ilangovan. So his both his teaching, okay, he's a very good teacher and he has a big fan following. Wherever he taught, and I know from the students there, the students really like his teaching, and not only teaching, he really follows up, and in the individual level, see, the students will have many problems, always may not be always really academic. So even teacher, as a teacher, we always cannot do that, but he manages to help them, encourage them, and so that goes in, because here also he people, students who for their UGC exam or UGC CSIR, he prepares them, helps them, and so not only these students, even see the senior faculty members and all who are his friends for many years now, they also need his suggestions and encouragement many times. Because going many years back in 89 or so, me and Professor Vasudhatta, we were postdocs in TIFR where Professor Ilangovan was there. So Professor Vasudhatta Datta, okay, he used to tell, if you are depressed and all, go to Professor Ilangovan. That time he didn't become professor. So go to his office, he will immediately come with his encouragement and looking things positively and all these. This is the thing. So on some other occasion, maybe I'll tell more things about Professor Ilangovan. So thank colleagues, and I'm handing it over to Ilangovan.
Thank you so much, sir. Thank you so much, sir, for enlightening us with your knowledge and speaking a few words about Dr. Ilangovan, sir. A warm welcome to all of you to the third talk of a mini series on Lie algebra. We also have Professor Satya with us today. Welcome to you, sir. Before we start our talk, there are some few instructions for the audience. At the end, when you are supposed to ask the questions, feel free to ask questions, but don't unmute yourself unless you are asked to do so. You can also write your doubts in the chat box or use the Zoom raise hand option in the Zoom feature, which is available. For those who are live on YouTube, you can text your questions in the chat box and we'll make sure that your questions reach to the speaker. Thank you so much. Over to you, sir.
Thank you. Thank you very much. Yeah, so thank you, Adhikari, for this introduction. I must tell if curry leaf as well as Adhikari, he may not remember these things. I am completing exactly 1 year here today. Last year, 17th August only, I joined here. So it is nice that he is introducing me to an audience as the first anniversary of my place here. There is a special reason also why I joined here on 17th August. That is the day I joined TIFR way back in 1978, 46 years back. So that is the reason I joined here also on 17th August. So now let us go back to Lie Algebras. So of course, before we start the main thing, one of the important things So one of the important things a student should not forget calculations. See, you know, till +2, mathematics was all calculations only. But at college level, so till +2, if your parents say others that you are a tiger in maths, that basically means that you are very good in calculations. And later on, concepts started coming. And then the problem is that so then students started doing mathematics like a zamindar. So they started becoming lazy. All they wanted to do was to sit and think mathematics only. But this is a very, very wrong attitude. As you know, at any level, calculation is very, very important. People who are just out of BSc may be happy that they are out of the labs, but still mathematicians do experiments. That is with various examples at a research level. You don't know whether a result is going to be true or false. The only way of finding a feel for the subject is through examples, and only then you get a feel. And develop an instinct also that way. Okay, so since last time we were doing enough calculations, today also we will be doing some calculations. Please remember this, all the students in particular. Mathematics Of course, concepts play a very, very important role, but that does not mean that you can stop calculating. Do your calculations. And last time we were doing this calculation about SL3, SLN. Okay, we were doing calculations to show that these are all simple Lie algebras. But the reason why it works is what we will see. This is a question we try to answer. Okay, in SL2, whatever method worked, we kept applying x again and again to get it to zeros all the way. So the same method works in general. The reason is this. So if you remember conceptually, one of the important things we did was to introduce eigenspace for a functional. We write SLN as H direct sum L alpha. H is the set of all diagonal matrices. And L alpha is set of all x in SLN such that Hx equal to alpha Hx for every. So this is what we did to generalize from eigenvalue. We generalized it to eigenfunctionals. For any alpha in H star, we can talk about the eigenspace corresponding. This is L alpha, set of all x in SLN such that Hx equal to alpha Hx. So this is the property. We take the Lie bracket of L alpha with L beta, we will end up inside L alpha plus beta. Okay, so this is the reason why that method works. As you keep applying the L alpha, we keep moving away further and further, and we are in a finite dimensional Lie algebra after all. So somewhere many coefficients will keep vanishing, and this is the method we apply to show that this is a simple Lie algebra. Let us verify this property, why this works. So L alpha plus beta is also an eigenspace. That's what we want to check. So let us take H in H, X in L alpha, Y in L beta. What we want to find is what happens to this. Okay, we want to say that this is going to be alpha plus beta of H, X comma Y.
Excuse me, sir.
Yeah.
Sorry to interrupt, but sir, the screen is not visible clearly. It's a bit blur.
Okay, it looks fine here. I don't know. Is it okay now?
Sir, if you can focus it more, it would be better.
Now it is better. At least
Yes, sir,
for me.
better.
Yeah.
Yes, sir, better than before.
Yeah, it looks better for me from here. Okay, so I continue. So what we want to say, x and y we are taken in L alpha, L beta. We want to say that the bracket belongs to L alpha plus beta. What we know is this. But black is better generally. Okay. Okay, Mr. Vikram says I should try blue because the black pen also is having some problem today. I will try black. In case it's not working, we will go back to black, okay? So this is the Jacobi identity. Okay, this is what we have, hxy plus x y h plus y hx equal to 0. And what are these things? Hxy plus y belongs to L beta, so hy will become beta hx, but here we have yh, so this becomes minus beta h. Okay, y is in L beta, so hy is beta hy. Now we have a yh here, so that became minus. And then here what we have? X belongs to alpha h, so hx equal to alpha xy. So if we take this out, what we get? hxy minus beta hxy plus alpha hyx. And in the last entry, we have a y bracket x. We have to make it as a x bracket y. So there also we get a minus sign. Okay. And if I take all these negative terms to the other side, we get what we want. Okay, so this is the first property of the bracket. If we take x in L alpha, y in L beta, the x bracket y becomes L alpha plus beta. And this is the reason when you keep applying same terms, x terms more and more, many of those coefficients will keep vanishing and we get this. So this is why okay, first we have proved that SL2 is simple, and I told you that SL3 or in general SL and simple, same method only works. The main reason is this: L alpha L beta is going to be contained in L alpha plus beta, and something more is happening here now. We have been using this adjoint only in general, so add is going from L to GLL, what we call as a adjoint representation. And we have seen already in the first lecture itself, I told you, and the last lecture we have seen already, any of these Lie algebras have so many copies of SL2. So we can restrict this add to SL2. And we would like to study this restriction now. So this restriction naturally leads to general theory, because adjoint representation we know L acting on L. Now inside L we are taking a sub algebra which is isomorphic to SL2. There are so many copies of SL2 we have seen. And so this leads to and as I keep telling you so many times, it's a very, very simple algebra. It's a fun kind of thing. Once you understand SL2, you can understand any simple algebra because there are so many copies of it sitting inside. Now, instead of just concentrating on the adjoint representation, we will try to study the general representation theory of SL2. Okay, I have already defined the representation, and I mentioned that for me GLN and GLB will be same. When B has a dimension n, we know that linear transformations can be identified with matrices, and when we have this, we say that V is a module over SL2. I have written the definition for SL2. Any Lie algebra, the same definition goes through, no problem. Module is same as representation of Lie algebra in GLV. One of the important and a very deep theorem tells us any finite dimensional module is going to be direct sum of irreducible modules. I should define what is irreducible, though it's obvious. I'm just giving a general definition now, better to give a general definition. Submodule means it should be a subspace and it should be left invariant under L. And
Sir, can you please turn your camera to the current board
next board.
where you are writing, sir?
I should call him 1 minute. board change. Okay, sorry for the thing. Now it's okay?
Yes, sir.
Yeah. Let me read the things again. Any finite dimensional module over a simply algebraized direct sum of irreducible modules. First, I have to give do definitions. What is a submodule? Submodule means it's a subspace such that XW is contained in W. Irreducible means the only submodules are going to be 0 and V. Then it's a irreducible module. So this Weyl theorem is a very deep theorem. I should make 2 comments. Of course, I have said that I am going to concentrate only on complex numbers, forget about other characteristics, but it's a good point to remark here. Characteristic P theory is still wide open. So plenty of research is waiting to be done there. Characteristic P, actually it is stuck for Vikram. It is stuck for a long time, around 50 years. People are trying it and not much success. So the characteristic P, if anybody is making a progress, naturally fame and fortune will be waiting for you. And another important comment, this is no longer true for infinite dimensional modules. And one of the important persons who studied infinite dimensional modules over a simple Lie algebra. It is wonderful that some Indian has played a very, very important role in the infinite dimensional module theory. He was a professor in TIFR, and after retiring 12 years back, he passed away. So, okay, so he has introduced what is known as Verma modules. So naturally, as you know, people who leave their legacy behind, they become immortal. And if you want to understand any kind of infinite dimensional modules, you have to study Verma modules. It is so basic in it, and it is useful in study of finite dimensional modules as well. But this goes beyond the reach of our series of lectures. I wanted to make a point to tell you all that one Indian has played a very, very important role in this infinite dimensional module theory, which is useful in finite dimension. For us, this is the most important thing. So any finite dimensional module over a semi-simple algebra is going to be direct sum of irreducible modules. So it is enough if you understand irreducible modules, then you know that direct sum of irreducible is all finite dimensional modules. So that is what we are going to study now. So now we will concentrate on study of irreducible SL2 modules, because once we know what irreducible SL2 modules are, we will know all the finite dimensional modules, because all finite dimensional nothing but direct sum of irreducible modules. Okay, so that is the nice thing about Weyls theorem. And recall SL2, this is what we have. The Lie brackets were calculated to be this. X is 0, 1, 0, 0, y is, this is a typo, this is h. H is 1, 0, 0 minus 1, y is 0, 0, 1, 0. We know that hy equal to h, hx equal to 2x, hy equal to minus 2y. And now let V be an irreducible SL2 module. Now we want to say that, so suppose we are having only one h, so we don't have to bother about eigenfunctionals. I just take some eigenvector. This is where we needed the complex numbers. Real numbers may not have eigenvalues and so on. So we take complex numbers so that we get always an eigenvector. Because we are in an algebraically closed field, eigenvectors always x. So what happens to x times v? What happens to x times v and what happens to y times v? I should mention here, before writing this, I should have mentioned actually. So sorry about this. So Suppose rho is the representation of SL2V to GLV. We write H times V to mean rho H. I don't know what notation I should use, X, Y. This is what usually people call as abuse of notation. Instead of rho T again and again, I am just writing T. So that is what I mean here. H times V means rho H times V. And when I'm writing H times X times V, that means rho H times V. And what is this going to be? Because it's a Lie algebra homomorphism, rho H, rho X is same as rho X, rho H, that's O HX. Okay, so this is the Lie algebra homomorphism. So H times X times V is X times H times V plus HXV. And what is HX? That is 2X. And what is HV? This is mu V. So what happens when I apply X to V? It has moved into the other eigenspace mu plus 2. If V is an eigenvector of eigenvalue mu for H, X times V is an eigenvector of eigenvalue mu plus 2. And you know similarly what is going to happen to Y times V. This is what will happen similarly. The calculation is same. Only instead of Hx, which is 2x, we will have a Hy, which is minus 2y. So that is why we will get H times Y times V is going to be mu minus H. And now we use the fact that V is finite dimensional. Since we keep on increasing the eigenvalue mu plus 2, mu plus 4, etc., this cannot go on forever. You know that eigenspaces, I should mention this maybe. Eigenspaces corresponding to distinct eigenvalues are linearly independent. Okay. Eigenspaces corresponding to distinct eigenvalues are linearly independent. So mu plus 2, mu plus 4, mu plus 6, etc. we will keep getting different vectors, but we have a finite dimensional vector space. So somewhere it has to stop, and this is the definition. Let us assume it to be non-zero. This is called the highest weight vector if x times v naught is 0. What we have just proved is that in a finite dimensional vector space, highest weight vector always exists. That's what we have proved. Okay, so now we start from this. Starting from a highest weight vector, we apply y now repeatedly. Y times v naught is v1, y square times v naught is v2, etc. I should tell you one important thing here. Sometimes students may get confused at this point because if you see y, what is y square? Y square becomes 0. But here I am happily writing y power I. That is because of this reason. Y square is a 0 matrix, so naturally it's going to be 0, but rho y square need not be 0. It is not a ring homomorphism. It's a Lie algebra homomorphism. Remember that very much. So now I have defined this. We have all these vectors vi coming from yi application. V naught is a highest weight vector. We keep applying y, and we have seen already. I have erased it, unfortunately. Here it is. When I apply y, the eigenvalue goes down by 2. When I apply y square, it will go down by 4, etc., etc. This way we keep going down. Before we write something, let us see what is this. This is the formula. X times vi is going to be I into lambda minus I plus 1 vi. So this is the claim. X times vi is going to be I into lambda minus I plus 1 into vi minus 1. So let us verify this. What happens to vi minus 1? Okay, we can take it if you want. V minus 1 also equal to 0, but we don't bother about that. Let us see v1 what it is. X times v1 is what? This x times y times v naught, and this is nothing but y times x times v naught plus x bracket y v naught. It's a Lie algebra homomorphism, so x times y is y times x plus Lie bracket xy, and we have started with the highest weight vector. By definition, x v naught is 0, and this is h times v naught, that is lambda v naught. Okay, so if you put I equal to 1, you see that this formula seems to be holding. Now by induction hypothesis, let x times vi be I into lambda minus I plus 1 vi minus 1. We have to see what happens to x times vi plus 1. Okay, we are trying to prove this formula for x into Vi. X into Vi, the claim is that it's going to be I into lambda minus I plus 1, Vi minus 1. First one we have verified and we have applied for induction. So now we want to see what is x times Vi plus 1. By definition, this is x times y Vi. Vi is y power I V naught. So Vi plus 1 is y power I plus 1 V naught, which is same as y into Vi. And again, we use the same formula. This is nothing but y into x Vi plus xy Vi. And now we have the formula x into Vi is I into lambda minus I plus 1, Vi minus 1, and this is HVI. HVI minus 1 is Vi. What is this? So Vi is applying I so many times. I know that this is what we get, because y once I apply, it becomes lambda minus 2. I times I apply, it becomes lambda minus 2i. Okay, so lambda minus 2i Vi is what we are getting. So if you add, what do I get? I get I plus 1 into lambda minus I square plus I minus 2i. So do we get whatever we wanted? I plus 1, I can take it out, and what we get is lambda minus I Vi. Okay, so this is what it is. If I put I plus 1 here, lambda minus I minus 1 plus 1. So by induction, the formula is proved. Okay, so this is simple calculation, repeated use of the fact that we are in a Lie algebra homomorphism, but it has a striking implication. Some kind of a magic is going to happen. You know, sometimes they say mathemagic. So what happens here now, since V is a finite dimensional vector space, there exists I such that Vi minus 1 is non-zero, but Vi is zero. All these are eigenspaces. Vi has eigenspace lambda minus 2i. All are distinct eigenspaces for H. And we know that we are in a finite dimensional vector space. All these are distinct, linearly independent vectors. So somewhere this has to happen. Vi minus 1 is non-zero, but Vi becomes 0. And what happens here? Vi is 0. So on the left hand side we are having 0. And right hand side we still have something I into lambda minus I plus 1. Vi minus 1. Vi minus 1 is non-zero, I is non-zero. So this is the remarkable result we are getting. 0 equal to I into lambda minus I plus 1 into Vi minus 1. It's a non-zero vector. I is non-zero. The only possibility is lambda minus I plus 1 should be 0. That means lambda equal to I minus. So this is the remarkable thing. So this belongs to Z plus. So if we take a highest weight vector of a finite dimensional SL2 module, the highest weight has to be a non-negative integer. Z plus is all non-negative integers. So this is the remarkable result we have got. Okay, so this is the remarkable result we have got. If you have an irreducible module and take a highest weight, that has to be a non-negative integer. It's a very, very important result, crucial result. If you have seen in all the SLN calculations, invariably we kept getting all integers only. This is the reason behind it. And if you take all these definitions, so we can take any arbitrary vector space and define this, what we have said, x into Vi equal to I into n minus I plus 1 Vi, where, okay, first I should have written that Ya into V0 equal to Vi, h into Vi is equal to lambda n minus 2i Vi. We get irreducible percentage. Okay, so this is the classification of all irreducible modules of SL2. And once we have this, as I told you, under the adjoint action of L, various copies of SL2 are there. And we know that any finite dimensional module is a direct sum of irreducibles. And so these are all the things occurring. All the weights, wherever they occur, they are all going to be integers. And in particular, all the eigenvalues are going to be integers. Okay, so this is how the SL2 representation comes out, and now we can state our main issue. This is what we want to see. Okay, this is our target for this mini series of 4 lectures, how to classify all simple Lie algebras. So I don't know how many of you have seen or read the novel. You know, this has been made into a movie several times in English, and it's based on a novel. So what is it is about? It is some doctor Dr. Frankenstein, a scientist, and he wanted to create something to help all the humankind. Okay, the rest of the life he spent trying to tame the monster. Unfortunately, he ended up creating a monster, and rest of the time he was doing this. So mathematicians are very similar. Luckily, it's not a monster that's going to do damage to the world, but once you created a monster, we want to tame it. So this is what happens in general from a idea of GLN, SLN, various algebras, orthogonal simplicity. We did not talk about it, I just mentioned it. We come into this definition of a Lie algebra, and now we are trying to classify all these Lie algebras. So this is what it is. So classification theorems are the most powerful in maths. Okay. So we only created all these things, but still, when we know that these are all the only things that we have created, that shows the mastery of mathematicians over their own world. So classification theorems naturally are the most powerful ones, and classification of simple Lie algebra is one such thing. And The important tool, of course, is going to come from adjoint representation. So if L is any Lie algebra, we have adjoint representation add going from. Okay, so now we are not anymore in matrices. Of course, I just mentioned the last time that A and B and C and D and these are all simple Lie algebras. Now we are having an abstract Lie algebra. The only technique we know how to handle abstract Lie algebra is using this adjoint representation. Now using the same adjoint representation, we are going to introduce a new tool. The tool that we are introducing somebody at the end of first lecture asked whether this killing form will make its appearance in this course. So now it is making appearance. The main tool that we are going to use is Cartan killing form. The definition is very simple. For every xy in L, define k of xy, k for killing, to be trace of add x, add y. So this is what is going to help us study the Lie algebras and simple Lie algebras in particular. This is the important theorem, again due to Cartan. For a simple Lie algebra, this killing form is non-degenerate. This is a theorem due to Cartan. And non-degenerate, all of you know, if every non-zero x is there, there is always a y such that kxy is non-zero. If people don't know, let me write it. Okay, so this is what is going to be useful for us. Onwards, we need to extend our definitions a little bit. If k is non-degenerate, L is direct sum of simple G. Okay, for the converse to be true, we have to extend it a little bit. Just a simple algebras won't be enough because it's natural. If you take direct sum of simple algebras, naturally k is going to be continuing to be non-degenerate, and that is why for the converse we extend the definition to simple algebra. This is the definition if you want. Direct sum of simple algebras is called semi-simple algebra. So I think I should stop now. I just make one comment here. At the end of first lecture, again, some people were asking about applications. Okay, so many of the physics people tell me, particularly statistical mechanics or string theory people, Lie algebras. Okay, and it also has some applications. Infinite dimensional Lie algebras, you differential equation and some Rogers Ramanujan identities, etc. Okay, so I am actually a pure mathematician. I really don't bother about applications, but at least within mathematics, it has some applications to differential equations and number theory like Rogers Ramanujan identity. Okay, so tomorrow we will start by exploring more about this scaling form. That is what is going to help us classify all simple Lie algebras. So thank you. Anybody, any questions? Okay, we'll ask them. Our technical help requests tomorrow's session starting a little late. Is it okay for people? 10 to 15 minutes late?
Okay, sir.
Today actually we started 5 minutes late. Is it fine?
Okay, sir. Yes, sir. About around 2:15?
2:15? Yeah, 2:15 is perfect.
Okay, sir. Okay, sir.
Okay.
As such, sir, there are no such questions, even on the YouTube live streaming.
Okay.
Thank you so much, sir, for giving us such an insightful talk and giving us some idea about the applications of Lie groups. And last but not the least, we always have a group photo at the end. So I request everyone to turn on their camera to have a group photo.
Many of them are still not on.
So I will count to 3. And on the third count, I request everyone to smile and we'll have a group photo. 1, 2, 3.
Thank you.
One more.
One more.
1, 2, and 3.
Thank you. Done?
Yes, sir. Thank you, sir. Lastly, I would also thank Professor Sukumar, sir, for being there. And I would also thank the audience for being part of today's talk. And at the end, last but not the least, I will be thanking to the backbone of this event, that is MTTS Trust and all the members of our organizing team of Curry Leaf. So thank you all of you. And here we will be ending our session and we'll be meeting tomorrow at 2:15 p.m.
Yeah, thank you. See you tomorrow.
So thank you, sir.